Imagine an object no wider than a typical city, yet containing more mass than our entire sun. To reach that level of density, you'd have to pack the entire mass of Mount Everest into a single teaspoon. Every star constantly fights its own crushing weight, gravity relentlessly pulling millions of trillions of tons of plasma inward. But the core performs nuclear fusion, releasing energy that pushes back against gravity, creating a stable balance that prevents collapse. A star survives only as long as this tug-of-war remains tied. But when that delicate balance finally breaks, the star begins its rapid descent into a far more compressed state of existence. For stars between 10 and 25 times the mass of our sun, the fuel eventually runs out. Once the core turns to iron, nuclear fusion stops entirely because iron cannot be fused to create more energy. With the outward pressure gone, gravity wins instantly. The star's entire weight implodes, rushing toward the center at a fraction of light speed. This violent collapse triggers a supernova, a massive explosion that rips the outer layers of gas away and blasts them into deep space. But the core remains. It is crushed inward until it hits the absolute physical limit of matter, the point where neutrons are packed so tightly they can no longer be compressed, stopping just short of becoming a black hole. This surviving remnant is the neutron star, a stellar core that has been compressed into the densest solid object in the known universe. On the surface, the pressure is so high that electrons are forced into protons, merging them into pure neutrons. This process of neutronization leaves the star composed almost entirely of uncharged particles. As the star shrinks, its rotation accelerates to maintain angular momentum. What once took weeks to rotate now spins hundreds of times a second. These objects remained theoretical until 1967, when radio telescopes picked up a series of highly regular periodic pulses that were so precise they were initially toyed with as potential alien signals. The signals were actually discovered by a graduate student named Jocelyn. Working with her advisor, Anthony Hewish, Bell identified the radio blips and ruled out instrumental errors or man-made interference. This slide shows the optical light curve of a pulsar, illustrating the periodic spikes in intensity Bell observed. These signals proved that the star was spinning rapidly, acting as a rotating beacon of energy. As seen in this illustration, a pulsar's magnetic field beams energy from its poles. Because the magnetic axis is misaligned with the rotation axis, these beams sweep across our line of sight like a lighthouse. Some remnants, called Magnetars, possess magnetic fields a quadrillion times stronger than Earth's, making them the strongest magnetic sources in the observable universe. The combination of rapid rotation and extreme magnetism turns the surface of a neutron star into an environment defined by forces that would instantly dissolve ordinary matter. If we move beneath the surface and into the crust, the pressure increases until individual atomic nuclei are squeezed so hard that they begin to touch. Protons and neutrons rearrange into complex sheets and cylinders known as nuclear pasta to survive the weight of the layers above. This pasta is likely the strongest material in existence. Even a mountain on the star's surface, only a few centimeters high, would be many times as massive as the Himalayas. Deeper still, at the absolute core, the density becomes so high that even neutrons can no longer maintain their individual identities. Particles may dissolve into a Quark-Gluon plasma, a fluid ocean where fundamental quarks flow freely rather than being locked inside protons or neutrons. Reaching this core means entering a state of matter that exists only under these specific, extreme conditions, where our current mathematical models of physics face their most severe test. Many neutron stars exist in binary pairs, locked in a tight orbit where they circle one another at a fraction of the speed of light. As they spin, they lose energy by radiating gravitational waves, actual ripples in the fabric of spacetime. This loss of energy causes their orbit to decay, drawing the two stars closer together. Eventually, the two stars collide in a kilonova. This explosion is one of the few events in the universe violent enough to spew neutron-rich material out into the surrounding galaxy. In the heat of this collision, heavy elements like gold, platinum, and uranium are forged from the star's remains and scattered into space. The precious metals found on Earth today were largely produced in these collisions. Rather than simple dead remnants, Neutron stars function as the primary source for the heaviest and rarest elements in the universe.